We'll start my presentation basically from the same point where I left you last year, and that is the automatic analysis of historical manuscripts, and in particular the automatic extraction of meaningful pictures from the decorations. And the sample result of the system we accomplished so far is this one. It's quite good. It's about 80%, 85% of recall and precision. Okay, and in the last year, and in particular this year, we will start to improve this system. And in particular, we start working on the commentaries, on the addition of textual information from commentaries. In particular, we try to extract, in the first instance, the most frequent keywords from the commentaries, and we try to see if there is some correlation between the most frequent keywords and the cluster of similar images inside the Bible. We saw some nice correlation. This is a sample in which there is the most common word is Jeremiah, and there is a large cluster of similar of pictures regarding Jeremiah with a similar appearance. So it is not a one-on-one match in this case, but we saw that textual information can be very useful, not only for the process of automatic manual and automatic tagging of pictures that we extracted, but also in the process of inclusion of search engine inside this application. In fact, if you look at the mock-up of the application I'm developing right now, there's a section right here in which I plan to include all this textual information, particularly the multimodal search engine that in my mind will take both the visual keywords and the textual keywords in order to filter the results and let the user to focus the research in a subset of images of the Bible. And just to say that this is not only a mock-up, an abstract mock-up, but that's a real application that I'm developing right now. These are some previous samples of the application. And okay, but the main accomplishment this year was not the high-level segmentation of these pages, but it was being accomplished in the early stages in the preprocessing phase. And in particular, there's an algorithm we need in the preprocessing that is the connected component labeling. And since we have high-resolution images with thousands of labels, we need a very, very fast connected component labeling to perform this one. And the connected components is a class of algorithms that just assign unique label to each connected component of the image. So it's a class of algorithms that basically whose performance is strictly dependent on the number of memory accesses on the image. So if you minimize the number of accesses to the image, you can maximize the performance of the algorithm itself. And for this reason, we propose this block-based connected component labeling with decision trees and decision tables. And what we've done basically is a very simple outline. We modeled the neighborhood exploration with the decision table. Then we convert the decision table into a decision tree, and finally from decision tree to C++ code in an automatic way. Everybody knows probably the decision table formalism, so conditions and action to be performed. You have to perform all these actions, all the actions marked as one when the that set of condition comes true. We introduce a slightly modification of this approach with the all decision tables, in which we have multiple actions, but we can, but these alternatives are equivalent. So basically, they lead to the same result in terms of connected components, but with different computational times. We include in this proposal an automatic selection of the best of these alternatives with an algorithm that we made in collaboration with Professor Montagero, and we include an algorithm that from the single entry decision tables we obtain with the previous one, we obtain an optimal decision tree, that is a decision tree with the minimal number of nodes, so the minimal number of condition checking, so the minimal number of access memory at last. The connected component labeling as a decision problem is an operation that takes 5 pixels, a mask of 5 pixels, the current one, and the 4 pixels around, PQ, R, and S. So we have 5 conditions in our decision tables. So a number of 2 at the power of 5 possible combinations. And as actions in this table, we can have no action at all, an assignment of, or the merge plus an assignment of the relative labels. And if we apply in a straightforward way these rules, we obtain a table like that. So a different action for each different situation, each different set of conditions. But if you take a closer look to that, we can see that there are some actions that are quite useless. For example, in the first example here, we should merge the label of P and the label of Q and assign the merge to X, but P and Q already shares the same label because it has been marked as equivalent in previous computational stages. So we can save a merge that is a computational expensive operation, just assign to X or the label of Q or the label of P. And if we apply the same concept to the, that's not a great thing. And if we apply the same concept to all other conditions in the table, we obtain from this table this one, which is a more compact way, more compact table with a lot of actions that are being removed because they are useless, and a lot of some equivalent actions. So we apply that the algorithm I mentioned just a few slides ago to select the optimal choice between the alternatives that are represented by the bold ones, and we apply the algorithm to convert to the decision tree. This is an algorithm proposed by Schumacher in the 70s to obtain this tree. No, another one. And we obtain this tree, and if you look at the charts, you can see that the performance gain is quite significant, just only using the decision tree from a standard approach for in different situations with different image sizes, so in different number of labels and so on. In this way, we basically reproduce the state-of-the-art approach for connected component labeling. That is an approach proposed by Hay in 2008. And we look forward to see if there is a faster way to accomplish the same action, the same task. And we thought about the thing that if you have a 2x2 block, all the foreground pixels are inside this block are 8 connected. So at the end of the computation, they must share the same label. So we thought about the possibility to extend the mask from the original 5-pixel mask to a wider 16 pixels mask. So we just write down the new decision table, which is much larger than the previous one because we have 2 at 16 possible combinations, and so we manually wrote it down. It was a little trickier than the other one, and we made it several times actually. But at the end, we assign all the actions, all the useful actions to all the combination. We pass the decision table to the algorithm to find out the most optimal alternative choice between the alternatives, and to the algorithm to create the decision tree. And what we obtain is this huge decision tree. We just test it down to see how fast it could be, if it was fast, and we obtain these amazing results. We basically save the 30. We made faster than the 30% of the respect of the state of the art, as you can see. And these very great results are just better than the state of the art in every kind of images, from the high resolution images to the standard resolution images. So it's an algorithm that performs better in any situation. And these algorithms, these performances are just more convincing if you compare our approach to the previous state of the art. And in particular, if you compare with the OpenCV algorithm that perform the same operation, that perform like this. It's a quite embarrassing comparison, if you, as you can see. So I'm finished with my presentation. These are my publication, in particular the one of this year. And in particular, I'm particularly proud for this line, first one, in which there is an acceptance for a paper in transaction image processing. This is one of the most important journal of our field. So I'm very proud of this. So thank you very much. If you have some questions.